Hi, my name is Shah, and I'm an MCAT tutor here with Shemmassian Academic Consulting. Today, I will be walking you all through a physics passage. Physics is an area that a lot of students often dread, but there are some strategies that make things a little bit easier, and a lot of it comes with practice and with effective content review. With that said, I'm going to go ahead and get started. I will be going through this passage slowly and carefully, just so we get the most out of going through it and reviewing it. Okay, so here is the passage. Let's go ahead and get started with this first paragraph. So, the blood-brain barrier, BBB, tightly regulates the flow of solutes into and out of the central nervous system. Due to its highly selective nature, the delivery of drugs and medications into the brain is non-trivial. Transcranial focused ultrasound, FUS, is a therapeutic technique that employs ultrasound waves to create cavitation bubbles, which disrupts the BBB and allows the passage of molecules into the brain. While FUS is a promising technique, its inherently disruptive nature requires the definition of safety protocols and the ability to modify ultrasound parameters nearly instantaneously. Okay, so that is a lot. It's helpful to sort of break it down, go through it one part at a time. With the first paragraph of science passages, it's usually an introduction, a background, and just general information setting up the experiments that are often brought in later. So here, the blood-brain barrier tightly regulates the flow of solutes. So this is introducing the blood-brain barrier. I find it helpful to highlight words that become acronyms later, just so it's easier to find it when it's mentioned in questions, and also if you forget later in the paragraph. Right, so I would highlight blood-brain barrier here, and this is introducing it. You should have come across it sometime in your MCAT studying in biology and psychology. And then it's mentioning this problem, right? So because it's highly selective, delivery of drugs is non-trivial, right? So it's a significant issue to deal with. Right after that, they present a potential solution, right? Transcranial focused ultrasound, right? So again, that becomes an acronym. I would highlight that. A therapeutic technique that employs ultrasound waves, right? Ultrasound waves are waves that are basically beyond the capacity for hearing. So that's about greater than 20 kilohertz. And then waves often come up in MCAT physics, so you should be familiar with sound and light waves and a bunch of vocab words related to that. So they create cavitation bubbles, which disrupt the BBB and allows, right? So this is a potential solution. While it is a promising technique, right? So they're presenting another contrast here, right? So this is a good transition word. While it is a promising technique, its inherent disruptive nature requires definition of safety protocols, an ability to modify ultrasound parameters nearly instantaneously. So again, presenting another problem. It's helpful to try to predict, right, what the next paragraph is going to be. We can predict with the way that this paragraph is ending that they might be able to present an experiment that looks at that or a potential solution to that. But this right here is, a problem that they're looking at. So we've broken it down. This is an intro, a background to the BBB, and a technique to deliver drugs. Okay, going on to the next paragraph. It has been previously observed that both subharmonic and ultraharmonic responses of bubble formation change during the course of FUS treatment. This is due to change in physical properties of microbubbles over time, including changing motions of trajectory in response to changing frequencies of administered ultrasound waves. Researchers wish to investigate cavitation and any features that signal the impending cavitation of microbubbles. Several experiments were performed using rat and macaque models, during which cavitation signals from microbubbles. The parameters for ultrasound emission during experimental trials are defined in Figure 1. Okay, again, a lot of information. Let's break it down. So this is they're presenting previous studies, right? They've found in the past that subharmonic and ultraharmonic responses change over the course of FUS treatment. And, you don't exactly have to understand what that means, right? A lot of times students get tripped up when there's information that they've never encountered before. They get worried like, oh my God, how am I supposed to go through the rest of the passage? What's important to note is, passages are for all science specialists, they're meant to introduce new information, right? You're not expected to know everything. What you can do is, one, use context clues, right? So give it some time, use the context clues of previous and coming up sentences to figure out what that sentence means, what those words mean. Another thing is, just let it be. It might, the questions might help guide you. It might not be something that you should be too concerned with. So, spend a little bit of time, maybe 15 or 30 seconds. If you don't get it, just move on. Okay, and then they're explaining why this happens, right? Change in physical properties of microbubbles, including changing motions of trajectory in response to changing frequencies, right? Because of the changing frequencies of the ultrasound waves from the FUS, there's changes in the microbubbles. Makes sense. Researchers wish to investigate cavity, right? So this is presenting what they're testing, right? Their hypothesis, their question, right? So a lot of times I find it helpful to highlight this because this is what the experiment is going to come back to, right? This is what the rest of the experiment is going to hinge on, the hypothesis, right? So they wish to investigate cavitation and any features that signal the impending cavitation of microbubbles. Okay, and then they're presenting the experiment, right? Several experiments were performed to test this hypothesis using rat and macaque models, during which cavitation signals from microbubbles were measured. The parameters are defined, right? So now we're going to the figure. If you don't always understand the words, sometimes it's helpful to have some sort of diagram, some picture, some table, right? In this case, we have a table. What do you do when you're presented with the figure? The first thing that you want to know is the title, right? So starting over here, we got one title. What is the title? Ultrasound emission and reception parameters used during FUS trials. Again, this just follows directly from this passage, right? So this is the title. This is what we're measuring. The second thing that you want to look at are axes, right? So here, the column, right? These are the different parameters. This is going to be emission central frequency, right? So emission, reception, pulse repetition frequency. So the frequency of pulses, like the number of pulses delivered per second, right? So frequency is cycles per second or number of times per second, measured in hertz. In this case, right, it's important to note the units. They're using megahertz, right? You should be able to know dimensional analysis. Right off the bat, you should understand that this is hertz times power 10 to the power of 6, right? That's mega. Okay, so this is regular, and then these are the analyzed ultraharmonic components, right? 1.5, 2.5, 3.5 of F naught. What is F naught? They don't define it, right? You can look the rest of the passage. It looks like they don't define it. This is something that you're expected to know coming in. F naught is going to be fundamental frequency, right? So I'll go ahead and type that. So that's going to be fundamental frequency. Okay. What is fundamental frequency? That is basically the lowest frequency of a periodic waveform, right? The lowest frequency it can go at. In this case, the periodic waveform is the ultrasound wave. Okay, so now you define fundamental. And it looks like F naught here is 650 kilohertz. So these are, and then we got number of time windows per pulse, right? This is just numbers. Okay, so now we've got this axis. This axis is rat versus macaque, right? So the difference, we're kind of comparing rat and macaque in this case, right? So those are the two axes. Now we've got what are the variables, right? We often, especially in experiments, we often distinguish them as independent variables, dependent variables, and also you want to be conscious of control, right? What are they keeping constant, right? So it doesn't confound the experiment, right? So in this case, the what are they manipulating, right? Independent variable is what are they manipulating. In this case, it's the type of model, right? So this is going to be the independent variable. These are the type of models. Dependent variable, what are you measuring, right? This is going to be the frequencies and the components, right? Those are going to be the dependent variables, right? That's going to be going down this way. These are going to be the two independent variables. Okay, so now we've got title, axes, variables. What's next? Next, we've got patterns, right? What are the patterns and trends that we notice? In this case, we're looking at numbers and we're comparing numbers, right? So here, emission central frequency, we've got 0.65, 0.5. You don't have to know exactly what these numbers means, right? Like, is that fast? Is that slow? You don't have to know. What you should be able to do is compare, right? 0.5 is a greater frequency than, 0.65 is greater than 0.5, right? So RAT model is greater in this case. Even in reception, RAT model is great, which makes sense. If it's greater emission, it's going to be greater reception. The pulse repetition frequency, the macaque model is actually 2 times greater than the RAT model, right? So you should be able to, compare and also determine sort of the severity or the extent of the difference, right? So that's 2 times. We've got 1.5. So, right, the analyzed components are the same, right? They are all relative to the fundamental frequency, but it's different fundamental frequencies, right? So macaque is 650. This one is going to be 500. And this is related to this emission central frequency, right? So we've got 650. And this is going to be greater than this 500. Last one is number of time windows per pulse. So number of time windows that they measured at per pulse. This is 55, 75, so this is going to be greater. Okay, good. So now we've sort of compared, we've determined the variables, patterns. What are we looking at here? Let's go on to the next paragraph. Ultra-harmonic frequency components of microbubble movement were monitored throughout FUS delivery, with analysis of frequency content performed between each pulse. This analysis was performed n times between each ultrasound pulse or at each time window. The frequency content determined in this analysis was used to adjust the ultrasound beam intensity. A representative example of frequency response patterns is presented in figure 2. Okay, lots of words. Frequency comes up a lot. Let's go ahead and break that down. It looks like they're kind of describing figure 1 and figure 2 in this, right? So they monitored frequency, ultra-harmonic frequency components, right? So this is what they're talking about, the analyzed ultra-harmonic frequency components between each pulse, right? And this is the pulse repetition frequency. So it's good to be able to compare the passage to the figures, right? Be able to connect them in some way. This analysis will perform n times between or at each time window, right? So number of time. So we got number of time windows per pulse, and perform n times at each time window. Okay, good. All right. And then frequency content was used to adjust, right? So this was what they were trying to test in the first place. They were trying to adjust modify the ultrasound parameters, right? So this is relevant right back to this hypothesis, right? Okay. And then they present an example in figure 2, right? So they're describing the experiment, what they're doing, what they're looking for. Let's look at this figure. Again, same things. What's the first thing that we want to look at? We want to look at the title. Frequency responses of microbubbles measured during FUS delivery. Again, directly back to this passage. Number 2, what's second? We want to look at the axes. What are the axes in this case? So we look at x-axis. What is this x-axis? Frequency in megahertz, right? So this is going to be x-axis. What is the y-axis? It's kind of hard to read, but here it's normalized amplitude relative to fundamental frequency, right? So it's not just amplitude, it's relative to the fundamental frequency or the lowest frequency. And it's measured in decibels, right? Which makes sense for sound. So that's going to be the y-axis. Another thing you should know is that there's 2 graphs here, right? What is the difference between the graphs? They mentioned that here at the top. So it's pre-destabilization, post-destabilization, right? Destabilization is after FUS delivery, right? Right, so now we've got the axes. what are the variables, right? So the axes give you two variables, right? One of the variables is frequency, the other variable is amplitude. On a third variable we have here is FUS delivery, right? We should be able to determine what is the independent variable, right? What is being manipulated? Oftentimes we look to the x-axis to determine what is being manipulated. In this case, though, the frequency is also being measured. What we are manipulating, though, is the delivery of FUS, right? So that's going to be the difference between these two graphs, right? So this is actually going to be the independent variable, and both of these, the x and the y axes, are going to be the dependent variables, right? And this amplitude is going to be dependent on the frequency, but they both are going to be dependent on this FUS delivery. Good. Okay, so that was the third thing, right? So we did 2, we did axes, 3, we did variables. Fourth thing, look at patterns. What are the trends? What do we see here? And how is this related back to the hypothesis, right? So pre-destabilization, right? This is basically going to be control. What is in this control? We see this frequency, right? This is the natural frequency of the microbubbles. And we see high amplitudes here, high amplitude here, and again right here. Okay, now let's compare that to after FUS delivery. We still see these same peaks right here, right? But we see 3 more high amplitudes, exactly where the FUS is delivered, right? So at 1.5 fundamental frequency, 2.5 fundamental frequency, and 3.5 fundamental frequency, right? So it looks like this FUS is disrupting it in a way where it increases amplitude. It's at the same frequencies, right? The frequency doesn't change, just the amplitude doesn't change, right? So it's still natural frequency. They're just increasing amplitudes or at these particular places. Okay, so now we've seen this on a pattern. Do we see any other differences? It looks like everything else is kind of the same. All right. And now we've got this last short paragraph. This is going to be the conclusion, right? Researchers concluded that unstable cavitation events can be monitored between pulses during FUS, and that ultra-harmonic disturbances appear when excitation bursts exceed a few milliseconds. So what does this mean? So let's go back to the hypothesis, or what they were looking for, right? They were looking to define safety protocols and modify parameters. They found that they can monitor between pulses, right, during the FUS, right? So it can be monitored, and that the disturbances appear when the excitation bursts exceed a few milliseconds, right? So this helps them define the safety protocols, right? So if excitation is greater than a few milliseconds, they see disturbances. Okay, good. So this is their conclusion, right? This is their results. Whenever you are presented with an experiment, and that's going to be often with science passages, there are 3 things you want to pay attention to. Right, so the first thing is the hypothesis. What are we looking for? What are we testing? What is their question? Second thing, the variables, right? What are they using to test this hypothesis? What are they manipulating? What are they measuring, right? What are their conditions? Third thing, what are the results? What are the patterns, the trends that we see in the figures? What are the conclusions that they make? And how does that relate back to the hypothesis? Okay, so here are the questions. Let's go ahead and start with this one. The ultra-harmonic frequencies used to analyze cavitation behavior and rat models are located at. Whenever you are doing questions on science passages, what you want to do is predict the answer before you look at the answer choices. And this can help limit any biases, prevent the word choices that they use to influence your answer choices, and make sure that you're thinking critically about the passage. So let's try to answer this before looking at the answer choices. It is important to know like the units, right? So units is something that often trips up students, where they can make silly little errors. So pay attention to units, and also make sure to write down units when you're doing any sort of calculations. Okay, so we're looking at ultra-harmonic frequencies used to analyze cavitation behavior in rat models. So we're looking at rat models. We know we're looking at figure 1. So we're going to be looking at this column, and then ultra-harmonic frequency used to analyze cavitation behavior. So which row are we looking at? take a second, look through the rows and try to determine which one you think would be best. And you should find that this is most relevant to the ultraharmonic frequencies used to analyze cavitation behavior. The units that they use is relative to the fundamental frequency, right? So they use 1.5, 2.5, 3.5 times the fundamental frequency, which is 650 kilohertz in the terms for the rats, right? We want to convert that into megahertz. Okay, so let's start with the first one, right? 1.5 times 650 kilohertz, right? So we can do 15 times 65. You want to make the math as simple as possible. The MCAT is never going to give you math that you can't solve without a calculator. And then we get 975. Make sure that you're paying attention to the fact that you did move one decimal point here, and you took out 1 0, right? So you would add a 0, move a decimal point, you would be back at 975, right? So now we've got 975. What are the units? Kilohertz. What are the units we need to get to? Megahertz, right? So how do we go from there to megahertz? Make sure you know the conversions, right? So it's going to be 1,000 kilohertz per 1 megahertz. And so we would move the decimal point another 3 places, and we would get to 0.975 kilohertz, right? And so let's see if we can eliminate anything with this. We can eliminate A, B. It looks like we see that here. We don't see that at D. So by just doing that math, make sure that you check your work. But it looks like we can eliminate all the answer choices except C. And the other answer choices look greater. And you can kind of see that it looks like it follows the trend, right? So 1, we get to C by process elimination and just doing simple math, making sure that we have the right units. Number 2, which of the following phenomena best explains the physical responses of microbubbles during FUS therapy? So again, before looking at the answer choices, what are the physical responses? What we find, right, is that changing motion of the trajectory, looking at the figure, we find that there's this, it continues, right, at its natural frequency. It continues at the vibrations that it usually goes at. It just has increasing amplitude, right? So just paying attention to that. Just going to the answer choices. So, go here. Okay. So constructive interference, what is that? Constructive interference is basically the interaction between two waves that are moving in opposite directions, right? So you can think of it as basically if one wave is traveling this way, the other way is traveling the opposite way. When they come together, right, constructive means they basically create a wave that has a higher amplitude than each of the individual waves, right? It's a combined amplitude of both of them together. It doesn't necessarily have to be at their peaks, but at any place, because they're adding onto each other, it's going to be a higher amplitude. That's constructive interference, right? In this case, the waves aren't actually traveling in opposite directions, right? We see one frequency, one wave, and the other one's just kind of disrupting it or coming in to interfere with it. So we're not necessarily seeing constructive interference here. So we can take that. Destructive interference, right? So that's the opposite of constructive interference. And that's often when one is at its peak, and another one is, at a trough, right? So they're coming, again, in opposite directions. In the middle, you'll see an amplitude that it's not necessarily going to be 0 always, but it's less than the individual wave amplitudes, right? And that's going to be, they're destructive, right? They're interfering with each other destructively. That's also not what we're seeing here, right? If anything, we're seeing an increase in amplitude at certain places, right? So it's not going to be this. Resonance. What is resonance? Resonance is a specific type of interference where one wave comes in, right? So we've got a wave traveling at its natural frequency, which I've mentioned a few times. It's just where it tends to oscillate at when it's vibrated or disturbed in any way, right? Another wave comes in and sort of affects that wave's amplitudes, right? Another wave comes in at the same natural frequency, right? So we've got one wave sort of traveling at a natural frequency, another wave comes in traveling at the same natural frequency, and so that when they come together, there is sort of this increase in amplitude, right? When that other wave comes in. And it looks like right here, right, when the FUS is delivered, right, when the ultrasonic wave is delivered, it causes an increase in amplitude at that same frequency. So that looks like that's what's going on here, right? We've got an increase in amplitude at this natural frequency. That is the definition of resonance. So we'll keep this, right? But we want to make sure to look at all of the answer choices before we choose something. So attenuation. What is that? That's going to be a dampening, right? A decreased intensity of a wave due to a disturbance, due to traveling through a medium. That is, again, not what we're seeing here. If anything, there's an increase in intensity, right? That we use amplitude to measure that. And so we're not seeing that. And so just going through all the answer choices, it looks like resonance is going to be the best answer here. Okay, moving on. Number 3, researchers analyzing a set of waves that are reflected from microbubbles note that the reflected frequency sometimes appears to be 1 to 10 hertz lower than the frequencies emitted by the FUS device. They can most reasonably conclude that something. Again, try to predict the answer choice, right? So it looks like the reflected frequency is lower, right? Or slower than, when it's lower, that means it's basically slower than the emitted frequency. What can contribute to that? And when we see something like this, something that should come to mind is the Doppler effect, right? Doppler effect is the fact that is when things are sort of moving, the reflective frequency, or the one that you tend to see or the one that we experience, is different than the one that is emitted by a particular object. And that is because of movement of objects toward or away from each other. And that's kind of what we're seeing, right? So we're seeing some sort of Doppler effect here. Okay, and it's only happening sometimes, right? It's not happening every single time. Okay, so going through A, the FUS device is defective. If we think about it, right, if the device was defective, right, that would affect the frequencies emitted, right? We've got no change in the frequencies emitted, and it would change the reflective frequency every time, right? Not just sometimes. So since it's only changing sometimes and we're not changing the emitted frequency, it looks like this cannot be the most reasonable conclusion. The measurement system needs to be recalibrated, right? So when there's a calibration issue, that means that it's not accurate, even if it is precise. In this case, it is not precise, right? We're not getting precise measures. It means that, again, when it's only sometimes appearing, right? If it were appearing every time, then maybe there would be a calibration issue. But if it's happening sometimes, that won't be a calibration issue. That won't be an error with the measurement, right? The blood-brain barrier dampens the reflected signal, right? So the blood-brain barrier is always going to be there. If it's dampening the reflected signal, it should be doing that every single time, right? And dampening, right, that refers to amplitude. Right now, we're talking about frequency, right? So we're talking about frequency, and we're talking about the reflective frequency being slower sometimes. That if it was C, then that would be happening every time, and we would be looking at amplitude. So it looks like C is not. So just by process elimination, we can get to D, but we want to make sure that also D is the correct answer, just to make sure that we eliminate it correctly as well. D, the microbubbles are producing a redshift effect. The redshift effect is a type of Doppler effect, right? So again, just when we predicted the answer choices, we thought about Doppler effect. And so redshift effect is a specific type of Doppler effect in which there's a slowing or a lower reflected frequency because it's moving away from the object that's emitting the frequency, right? The device, in this case, the device. So if the microbubbles are moving away from the device, right, there is some sort of movement that might cause a redshift frequency sometimes. So this is going to be our best answer choice. Good. Okay. Number 4. How many times were the frequency responses of microbubbles assessed over a 1 second time period? So they describe these parameters in figure 1. So we would be going back to figure 1. And what were we looking for? We're looking for the number of times, right? So number of times frequency responses were assessed over a 1 second time period, right? So times per second, right? That's basically our unit. Okay, so here we're given frequencies. We're not really looking at frequency, pulse repetition frequency, right? This is the number of pulses per second. So we've got pulses per second here. We got analyzed components, and we got number of time windows per pulse, right? So basically number of times per pulse. Right, so if we combine these two, right, if we have pulses per second and number of times per pulse, right, we can cancel out per pulse and we'll get number of times per second, which is the unit that we're looking for. How do we combine them? You multiply them, right? So if you multiply them together, you would be able to cancel out pulses. So we've got 5 hertz, again, paying attention to units, we got 5 hertz and we got 55, right? So we got 5 times 55, and right now we're looking at just the rat models. Here they said rat and macaque, right? So we're going to start with the rat and see if we can eliminate any answer choices before having to do more calculations. You want to do as little calculations, spend as little time as possible. All right, so 55 times 5, we got 25. 5 times 5 is 25, 275, right? And what are the units here? We got times per second for the mouse model. Okay, so let's just go to our answer choices. It's not going to be 55, right? Because we have to multiply that by the number of pulses per second. It's not 650, it's not 1.3, right? This is less, 275. That's the answer we got. We can also check the macaque models, right? But the macaque was 75 times 10 is going to be 750. Right? So we got to D with process of elimination, just doing one simple calculation, but making sure that you're paying attention to units, right? Getting to the right units at the very end. And understanding that hertz is per second. Okay, let's go to our last problem. The speed of sound through the brain is approximately 1540 meters per second. What is the expected wavelength of an emitted ultrasound signal traveling through a macaque brain, right? So we got a few different parts here. We got speed of sound, right, which is going to be V. We got expected wavelength, which is going to be this. Emitted ultrasound signal traveling through a macaque brain, right? So macaque, again, going through this figure, we're looking at, I'll use a different color. We're looking at macaque. We're looking at emitted frequency, right? So that's going to be this one. So we look at emitted central frequency. You got 0.5 megahertz. So we've got a couple of numbers. So we got speed, we got wavelength. The number we have here is 0.5 megahertz. How are wavelength, speed, and frequency related? You should know that formula, right? This should be in your head. Speed equals frequency times wavelength, right? Or wavelength times frequency. Okay, what information do we have here? We have speed at 1540 meters per second. Again, write the units. And we have frequency, but it's in megahertz, right? So we need to convert that to hertz. How do we convert that to hertz, right? Megahertz is times 10 to the power 6. So we got, if you want to do it in scientific notation, right? If we were to move this one point, we got 5 times. Again, do it in a way that works best for you. This works best for me, so this is how I'm going to write it. So we got 5 times 10 to the power of 5 hertz, right? So this is our frequency, and now all we need is wavelength. And how do we find wavelength? We divide. So we're just going to divide 1540 divided by 5 times 10 to the power of 5. So we can ignore the exponent or this log right now. We can do 1540 divided by 5. We'll get 308, right? Okay, so this equals 308. And since the 10 to the power of 5 is the bottom, it's going to be 308 times 10 to the power of -5. What is units? Meters, right? So we had per second here. So we can eliminate those. We got meters. Okay, 308 times 10 to the -5. Okay, so let's just go back here. The only one that closely resembles it is 3.08, but we've got different number here, right? And this is in scientific notation, right? So we can change this to scientific notation. If we were to move 2 decimal points here, right, we would get 3.08 times, right? You move 2 decimal points to the left, you decrease this by 2. So it's helpful to be familiar. You want to be very familiar with scientific notation, with dimension analysis, things like that, right? So now we've got scientific notation, and that is exactly what we see here. Okay, good, right? So we do the calculation before we look at the answer choices. We can eliminate everything else. We know, right, it's not going to be greater. It's not going to be such a high wavelength, right? It's going to be small. Okay. So that's all. I hope this was helpful. I went through it very slowly. You want to be going through passages at 8 minutes, but when you are practicing, it's helpful, especially when you're reviewing, to go through each answer choice, to go through the passage slowly, make sure that you understand each word, so that when you're actually doing the MCAT, you're able to go through it quicker, you're able to be more efficient, especially going through figures and understanding, different words in context. If you enjoyed this walkthrough, please be sure to like this video and subscribe to our channel so that you don't miss out on future MCAT videos. Be sure to also check out our high yield strategies in our MCAT 528 series, and click the link in the description to sign up for our practice questions so that you get every last bit of practice before test day. Happy studying!